Screencast 20.16. Let's calculate the equilibrium constant for a cell. This could just as easily be a single replacement reaction. Doesn't matter, but in either case we can divide this thing up into its oxidation and reduction half reactions. Tin is being oxidized to tin 2 plus. Copper ions are being reduced to still copper ions, but from 2 plus to 1 plus. And so there's the oxidation reaction. We're simply going to look up the reduction potentials for these on a table and flip the value for the oxidation half reaction and then combine the two, which should work fine. So we find a value for that. We've reversed it. Here's the standard reduction potential for copper 2 plus to copper 1 plus. And we combine them and get a standard EMF for the cell of 0.3 volts. Remember, we do not use these coefficients as multiples. Keep them just like they are for electrochemical cells. Now let's find the formula that involves electrochemical cells and K, the simplest form of which is this. That 0.3 volts will be equal to 0.0592 volts divided by the number of electrons involved times the log of that K value, which is what we want, right? The equilibrium constant. So why don't we separate this into log K equals and get this part of it over on the other side. We do that by multiplying both of them by the inverse, so it'll cancel on this side and flip it over on this side. And there it is, flipped over, right? Log of K is equal to E of the cell, and flip that over, ends on top. 0.0592 is on the bottom. We know this number, it's 0.3 volts, we just calculated. We know the number of electrons involved are 2. And we know that this is just a number. And therefore, the log K is equal to 10 to 14. And then when we solve for K, we simply get a very high number. 1.38 times 10 to the 10th. This is a highly favorable rate constant. Screencast 20.16.